So now that we have discussed most of the relevant materials on probability theory that we require in our course, we want to discuss something which is very, very significant, which is the central limit theorem. As we shall see later, this has quite a application, or is one of the pillars of statistical mechanics. Now, essentially, suppose I have n random variables which are mutually independent. They are mutually independent, and let's denote them by x1, x2, xn. The associated probability densities are wx1, wx2, wxn. So the form of w is same for everybody. Same. Essentially, they are drawn from the same distribution, but they're mutually independent, right? So then let's define a variable which is x1 plus x2 plus x3 all the way up to xn. So given this probability density is w, I want to know what is the probability density py of y, right? Now for that, let's construct this variable which is sum over I minus average of x divided by square root n. And if you just expand this now, this becomes xi over square root n minus square root n times average x, which is nothing but y over square root n minus square root n times average x. So we'll go over to this quantity, we'll evaluate this quantity, but slightly in an indirect way, and it will you will see the significance of this. Right now what I want to say is that I have never given you the form of w, and we will see later whether we need it or not, and that is kind of an essence in this whole story. So let's write down pz, or since I am denoting it with w, so wz of z. Then wz of z is of course dx1, dx2, dxn, wx1, wx2, wxn, right? Not only that, now I also have to make sure that z has this particular form, which means z delta z minus y over square root n plus square root n times average x. So let's compactify our notation a little bit, and we write down wxi product, right? And this delta function, I want to replace them in an integral representation to the power I k z minus y over square root n plus square root n times average x, right? So I have product over I dxi w of xi, and if I look at this over here, square root n times average x, and I have minus I k y over square root n. Let's change the integrals now, the order of the integrals, and we will write down this as dk over 2 pi I k z plus square root n times average x product over I d of xi w of xi e to the power, if you now replace y by sum over xi and like this, then if you inspect this more carefully, then you see that this, since this is in the exponential, this also becomes a product, and therefore I can write down this part as dxi wxi e to the power minus ik square root n xi. If you recall this, then this is essentially the definition of your characteristic function. We had defined it with the +1, but you can as well define it with the -1. It all depends on how you define your delta function. I can define it the delta function also with minus ik. So now, therefore, phi k, the other way down, let's say. So phi of xk is average of e to the power I kx, which is integration dx wx e to the power minus ikx, right? So if I do the mapping, if you look at it carefully, then this integral, the product of this integral at wx1 e to the power ik square root n x1 dx2 wx2 e to the power minus k over square root n x2, so on and so forth, all the way going up to xn. But the form of w is the same. That's one of the advantages that we have in our discussion. So I can clearly write down this as phi of k over square root n, and therefore this whole integral, the product of this integral, becomes this raised to the power n. So wz of z is essentially dk over 2 pi e to the power ikz plus square root n. There is an ik missing somewhere. There is an ik here. Phi of k square root n raised to the power n, right? We will assume now that n is large, right? Before proceeding, so let's just look at ln of phi k. Then ln of phi k is ln of average e to the power minus ikx, right? Which is log of 1 minus ikx. There's an average outside, and then you have plus ikx whole square over 2 factorial, so on and so forth. Average closes, and this you can see that this is 1 minus ik average x. I square is minus k square x square over 2 factorial, and higher order terms, right? This I can write down as minus ik raised to the power m cm over m factorial. M is equal to 1 to infinity. This quantity is called a cumulant of the distribution or the density. So C1, for example, is average x. C2 is average x square minus average x whole square, which is the variance. And you can clearly define the other coefficients as well, other cumulants from this definition, right? So now I have this ln of phi k looks like this. So therefore, if I am careful enough, phi k is e to the power sum over m equal to 1 to infinity minus ik raised to the power m over m factorial cm, so that I can write down this as minus ik. The first one is average x, the second one is plus ik whole square over 2 factorial sigma square minus ik whole cube c3 over 3 factorial, so on and so forth. Now recall, I have phi k over n. What I have in the expression, I have phi k over square root n raised to the power n, which means this is I k over square root n average x plus I k over square root n whole square 1 over 2 factorial sigma square 1 over 3 factorial I k over square root n whole cube C3 whole raised to the power. There is of course other terms raised to the power n. So if I carefully do this, this becomes minus I k square root n average x minus half k square sigma square. This becomes n independent minus 1/6. This is I, right? K cube. So this becomes I cube, I square is minus 1, so this becomes plus, and I have n to the power 3 half, which I am raising it to the power n, becomes square root n C3 higher order terms. Now let's come back to this WZ. So the WZ, the density that we had, probability density for the variable z we were calculating, had the form dk over 2 pi I k z plus I k square root n average x, and I had phi over k over square root n raised to the power n. So this becomes dk over 2 pi I k z plus I k square root nx, and then I substitute this expression, or rather the second one, into this and write it down as square root n times average x minus half k square sigma square plus I by 6 k cube square root n C3, then higher order terms. Of course, this and this cancel out, and then now if we take the limit of n to infinity, which means my number of variables, the independent random variables that I started off with, is really a large set, then all the other terms vanish because they decay as 1 by square root n, then the next one will be n to the power 3 half, so on and so forth, and essentially wz of z is going to be left out with dk over 2 pi e to the power I k z minus half k square sigma square. All we have to do now is we have to integrate over k, and once you do this, you will see that this integration is going to give you z square over 2 sigma square. So given that I have wz, I want to calculate the p of y, right? But so I use that by using the relation, because it's a transformation, so that wy, capital Y of small y, is wz of z dz dy, right? And once you do that, you are going to get this as square root 2 pi n sigma square e to the power y minus n average x whole square divided by 2n sigma square. So that average of y is n times average of x, and sigma square is n times, so sigma square y is n times sigma square x. But remarkably, you see, this probability density for y, which is now a sum of random variables, comes out to be a Gaussian irrespective of the form of w that you choose. So this is one of the part of the central limit theorem. The second part is, of course, average of y is n times average of x, right? And sigma square y is n times sigma square x. Therefore, average of y divided by sigma y, sorry, the other way around, it has to be sigma y divided by average of y is going to be square root n sigma x divided by n times average of x, which is 1 over square root n sigma x over average of x, right? So this tells you, say sigma x and over average of x is a number, right? It does not depend on n, but what it essentially tells you that if you keep on adding these numbers n1, n2, these random variables x1, x2, x3, xn, then the variance of y to the mean, this ratio, will decay as 1 by square root n. So clearly, I know that first of all, this probability density is going to be a Gaussian. So let's look at it. So it has an average, which is n times average of x, and it has a certain width, which is sigma y. So if n is large enough, then not only does this ratio decays as 1 by square root n. So the average also increases, but the sharpness of this, which is essentially the spread of this curve, also decreases. So this curve becomes more and more sharper and sharper, right? So this is the consequence of the central limit theorem. Now, where do we use it in statistical mechanics? Well, as we shall see later on, see all thermodynamic quantities that we have calculated for a hydrostatic system, for example, the energy, right? Extensive quantities, the energy I can always write down as energy of the constituent particles, right? Now, because of that inherent molecular chaos in such a system, these quantities are essentially fluctuating in time and therefore they are random variables. Consequently, it tells you that irrespective of the distribution of the individual energies of the particles, the macroscopic energy E will have a Gaussian distribution, and that is a consequence of your central limit theorem. So the central limit theorem is extremely powerful, and we shall exploit its power later on in statistical mechanics. So we learned about probability, the parts which are necessary for us, including discrete distributions and continuous distributions. The rules of probability, interpretation in terms of frequency, and symmetry, the conditional probability, and how one goes from how one defines a continuous random variable and therefore a continuous probability density. We also looked at the central limit theorem, but right now what we are going to focus on is information and uncertainty. Suppose I give you, so let's just write information and uncertainty. Now suppose I give you an experiment. For example, the first experiment is I toss a fair coin. Then I know the outcome of this is head and tail with equal probability of half and half. The second experiment that I do is toss a biased coin. Now once I toss a biased coin, I will still get the same outcomes, head and tail, but the probabilities will be slightly different, in the sense, let's say P is 1/3 here and P is 2/3 here. Probability is 2/3 here. So clearly of these two, if you want to ask that in which of this experiment the outcome is more uncertain, then you will say experiment number 1, because both of these events are equally likely to happen. In the second experiment, of course, this is not true, because you know that the tail is most likely to appear more, right? Now let's do a third experiment where you roll a 4-faced die, and the outcomes you know are 1, 2, 3 and 4. If you are now asked to compare between these three, then you will say, oh, experiment number 3 is. So now when you are asked to rate these 3 experiments based on the uncertainty on the outcomes, then you will say, look, for experiment number 3, the number of outcomes are more. Therefore, I do not know. It's more uncertain for me to predict which outcome is going to come. So of these 3 experiments, number 2 is the least uncertain. If I now want to do a 4th experiment where I roll a 6-faced die, then you are immediately going to realize that the outcomes are not it doesn't have 4 outcomes, but there are 6 outcomes, and therefore this seems to be the most uncertain experiment that we are doing, because we cannot predict very surely which outcome is going to come. So if you were to rank these experiments, then experiment number 4 would be most uncertain, and experiment number 1 would be least uncertain. I do not know how to rank experiment number 3 and experiment number 1. So the idea is now, therefore, to develop a measure for this uncertainty, and let's call this measure as S, and let us denote the probabilities P1, P2, Pn if there are n outcomes of the event. The idea now is, in the very first case that we discuss, or we try to figure out an expression for S, we will assume that all the events are equally likely to appear. If this is the case, then if omega is the total number of outcomes, then the probability, since the probabilities of these outcomes are equally likely, therefore Pi is 1 by omega. The associated probability for each of these outcomes is just 1 by omega. For example, for a fair coin, we saw that the probability for head was half, tail was half. For a fair die, we rolled 4-faced die, we know that the probabilities are 1 by n. So that's the same thing that we are applying over here. We will first assume that all these events are equally likely to appear, and therefore all the outcomes are equal a priori probability, and that probability is given by 1 by omega. So this expression therefore now reduces to S of omega. Correct? So now it's clear. Let's what characteristics of that S will have. If omega is equal to 1, then S of omega is equal to 1 is 0. What does this mean? Omega is equal to 1 means essentially there is only one outcome, and for that event you know that that is the only outcome that can appear, so there is absolute certainty. There is no uncertainty associated with that, right? And as we illustrated over here, when we looked at experiment number 3 and experiment number 4, if there are two events whose outcomes are omega 1 and omega 2, such that omega 1 is greater than omega 2, this would imply that S of omega 1 is greater than S of omega 2. So the more the number of outcomes you have, more uncertainty you have in that experiment, right? This is just intuitive knowledge of the phenomena, right? Now let's now say that with these tools, with this information that I have in my hand, let's say I have two events with outcomes omega 1 and omega 2, and I do them simultaneously. So the total number of outcomes are omega 1 times omega 2, right? For example, I can toss a coin and roll a die, right? So now I want to know what is S omega. Clearly, if I know the outcome of one of the event, then the uncertainty in the other is not completely gone. For example, if I toss a coin, then I have head and tail, and if I roll a die, I have four-faced die, let's say, I have these four outcomes, right? So even if I know the outcome of the tossing event, tossing of the coin, I still do not know the outcome of the rolling of the die. There is uncertainty which is contained over here. So it follows that I have must be equal to S of omega 1 plus S of omega 2, right? Now, if I just look at this functional expression that I have written down over here, based again on our intuitive analysis, then it follows that there is a very definite functional form for S which will obey this. So if I have x and y is equal to S of x plus S of y, then there is a very definite functional form of S. So I want to know what that is. That is not very difficult to do. First of all, we write z is equal to xy, right? Then del sz del x, which essentially means that I'm just looking at the left hand side and trying to calculate these quantities, is del z del x ds dz, right? And del z del x is y ds dz. If I do the same thing and write down del x del s of del y, just looking at the left hand side, then I know that this is del z del y ds dz, which is equal to x ds dz, right? Good. So we'll keep this in our hand. But now, if you're operating del del x on s of z, is like operating del del x on the right hand side also. So del of sz, del of x, by this expression that we have written down over here, is ds dx, and del of sz, del of y is ds dy, right? So it follows that ds dx is equal to y ds dz, and ds dy is equal to x ds dz. So which means I can just write down ds dz and put 1 over y over here and 1 over x over here, so that 1 by y ds dx is equal to 1 over x ds dy, which would imply x ds dx is equal to y ds dy. Now the left hand side and the right hand side, the left hand side is a function of x, the right hand side is a function of x, and therefore this can only be a constant, which means that s of x can be a ln x, right, plus b. Since s of 1 is equal to 0, the one that we written down over here, that if omega is equal to 1, the uncertainty associated with it vanishes, it follows this would imply that S of x is a ln x. Hence, our measure for this entropy becomes a ln omega. And since a is arbitrary, we set a equal to 1, so that our expression of this uncertainty becomes ln omega. This is the expression for the uncertainty for events where outcomes are equally likely to occur. So that means all the outcomes have equal a priori probability of 1 by omega, right? So now that we have developed an expression for the uncertainty in the outcomes of an experiment where all probabilities are equal and pi is 1 over omega, right? But we want to now focus on the cases where my probabilities of the outcomes are different. What happens to this S? How do I write down an S? For example, consider a loaded die. Essentially, that means that a die which is not fair but a biased die, where probabilities Pj associated with the outcome omega j, right? Which the set of omega j's are the numbers 1, 2, 3. So if there are n, it's an n-faced die, you know that there are n outcomes. Now what we do is we roll this die a large number of times. So roll the die a large number of times. Say n, right? So what is going to happen? Then each outcome is going to appear. You have an outcome. Omega j appears nj times such that you can pj times n is nj. This is what follows from the frequency interpretation of the probability, or alternatively you can write down pj as nj over n. We shall use this later on, right? Now the outcomes can occur in different order, right? But so when you roll the die n number of times, you can expect that the outcomes that will come in different order. Therefore, the original uncertainty about rolling a die for one single event, when you are rolling the die only once, has now been transformed into the uncertainty of the order. However, all the orders are equally likely to appear. So all the orders, so what you had started off is essentially asking the question that what is the uncertainty in the outcome, right? And that now I have transformed into a different question, that what if I roll it n number of time, what is the uncertainty in the order? Because my outcomes can appear in different order, and therefore you expect that if you roll it say 10 times, then you're going to, or 100 times or 1000 times, you're going to get different orders in which this is the outcomes are going to appear. But therefore your original uncertainty about the outcome has now transformed into the uncertainty in the order. But all the orders are equally likely to appear. They appear with the same probability. So all you have to do is you have to figure out the total number of possibilities that you can have, right? And we will call this as omega r, clearly n factorial, n minus n1 factorial, n1 factorial times n1, sorry, this has to be n minus n1 factorial, n2 factorial, n minus n1 minus n2 factorial. All this way it is going to go. So finally you are going to have, if there are n such events, n such outcomes, you are going to have n minus n1 minus n2 and here you are going to have n1 minus n2 minus n minus 1 factorial, right? This is like nc n1, and once you have chosen nc n1 number of balls, you are left out with n minus n1 of them, and then you choose n minus n1 c n2, so on and so forth, right? So it follows that this is going to cancel with this is going to cancel with the next term, and this is going to cancel with the preceding term, and n is n1 plus n2 and n, so that this is essentially a 0 factorial. So you are going to be left out with product over n, product over j, nj factorial, right? These are the total possible orders that you can have, right? Think about this. This is just a combinatorics problem. It's not very difficult to understand. But all of these orders are equally likely to appear, right? So therefore, the associated uncertainty we just calculated is omega r. We will just put a subscript n here to say that this is not actually for a single event, but for n rolls of the die. Correct? So therefore, this becomes ln n factorial minus sum over j ln nj factorial, right? And if I use Stirling's approximation, then this is n ln n minus n minus sum over j nj ln nj minus nj, right? So I'm going to have minus nj ln nj. I'm going to have plus n ln n minus n minus sum over j nj, and this is equal to, so this is going to be plus and this is going to be n, so that you are going to be left out with minus sum over nj ln nj plus n ln n, right? nj is n times pj. So I can just so let's n times pj ln n times pj plus n ln n. Now you can immediately see where this expression is going to go. I can open up the log here to write down ln plus ln pj, so that the first term is going to be minus n pj ln n plus, sorry, this is minus n pj ln pj with a sum over j plus n ln n. This becomes minus n ln n, sum over j pj is 1, the normalization condition, and you have a plus n ln n, and you're left out with minus j, this last term. So therefore your Sn is minus n sum over pj ln pj, right? It follows that I know that the uncertainty associated with n rolls of the die is this. What is the uncertainty associated with one roll of a die? That becomes Sn over n. The original answer that we are looking for, except one has to take care that n is very large, and you finally come up with the answer pj ln pj. So this is the measure of your uncertainty when the probabilities for the outcomes are all different. If I now want to see whether I'm right in doing that, I can always take Pj as omega by omega, so that S becomes minus, we will keep sum over Pj here, ln omega, which is ln omega. So we recovered the earlier result for equal a priori probability that we had derived before. So the general expression for an uncertainty associated with the outcomes of this is minus Pj ln Pj, right? As we shall see that this one has a very, very deep connection to statistical mechanics, right? Now this statistical entropy, so what we call this is, we call this as the statistical entropy. And this statistical entropy has certain characteristics, right? So first, let's say, let Pi and Qi be two probability laws. Right? So then we consider Pi ln Qi minus sum over Pi ln Pi. Correct? So this quantity, now I can very nicely write down this as sum over ln Qi over Pi. You will see in a moment why I judiciously chose my left hand side. It's essentially I'm motivated towards a certain thing I want to show. So Pi ln Qi. Now I know that ln x is less than equal to x minus 1. Therefore this sum is less than equal to sum over Pi. X minus 1 would be Qi over Pi minus 1, which is sum over Qi minus sum over Pi. But Pi and Qi are two probability laws. Therefore, they must satisfy normalization. Therefore, both the sums that you see over here, this one and this one, are 1, so that this is less than equal to 0. Therefore, it follows from this little derivation that we did that Pi ln Qi minus Pi ln Pi is less than equal to 0, right? For two probability set of laws. Now choose Qi as 1 by n, which means that this corresponds to equal a priori probability, right? If that is the case, then I have sum over Pi minus ln n minus sum over Pi ln Pi is less than equal to 0. But sum over Pi is 1 in this particular case. Therefore, I have minus ln n plus S of Pi, the entropy, the statistical entropy associated with the probabilities Pi must be less than 0, which means S of Pi must be less than ln n. Therefore, there is an upper bound to the statistical entropy that we have calculated, and the upper bound corresponds to the case where all probabilities are equal. All the outcomes are equally likely. So for a fixed, but one has to be careful that the number of events or the outcomes are the same, right? So which means for both these probabilities sets, the number of outcomes are same. So for example, one can think of let Pi correspond to the probabilities associated with the rolling of a biased die. It can be n-phased, and Qi corresponds to the rolling of a unbiased fair die, right? So in this case, Qi is 1 by n, and that gives you the upper bound of the statistical entropy. As we learn thermodynamics, we will see that this particular choice is what is called a microcanonical ensemble, right? So when we do microcanonical ensemble, we shall use this expression for the statistical entropy to build on the thermodynamics.